Hello everyone. Um, my name is Ese, and I'm going to be walking us through this workshop on software engineering best practices for data scientists and machine learning engineers. So a little bit about myself. My name is Eseoghene Emuraye. You just call me Ese. It's easier to pronounce. And I'm a graduate student of data science at the George Washington University in Washington, D.C., currently in my third semester. And at the George Washington University, I work as a graduate teaching assistant, assisting my professor in natural language processing, where I assist students and grade assignments as well as exams. Over the summer, I worked with IBM as a cognitive engineer consultant and grad intern, basically as a data scientist. And I work with solving problems in New York State government. And also I'm a statistical consultant with the George Washington Library and Academic Innovation via provide consultation in programming, statistics, and machine learning. Yeah, my favorite way to pass time, it's going on hikes and exploring nature and also playing the piano. I recently started learning how to play the piano. And I'm more active on LinkedIn and Twitter, so those are my handle. Okay, so I think with that we can move ahead with the business of today. So we're going to go through this workshop, going through this outline. So the learning objectives, and we'll then ask ourselves, why do data scientists and machine learning engineers, why should we adopt software engineering best practices? Why is it important in the first place? And then, having understood that, we'll move on to like understanding the scope of work for data scientists and machine learning engineers, which is basically into two phases: the model experimentation and development phase, as well as the MLOps phase. And then we're going to walk through a case study together and try to see how we can implement some of the best practices or software engineering best practices that we've highlighted in the course of the presentation, and walk through the case study. And I hope that at the end of this workshop or this presentation, we'll be able to like learn more about how best we data scientists and machine learning engineers should implement best practices and then key takeaways. And so there are basically two learning objectives for this course. First is to understand the roles played by data scientists and machine learning engineers in a team, because actually the data scientists and machine learning engineers do not work in isolation. They always work in a team. More often than not, you work in a team. And so we need to understand the role played by data scientists and machine learning engineers, and then gain basic understanding of essential software engineering best practices. So why back to the question I raised initially, why do data scientists and machine learning engineers, why should we adopt software engineering best practices? So the famous diagram here, the draconian data science Venn diagram, summarizes a lot of things about what data science is all about and machine learning. At the core of data science, you need to understand, like you need to leverage knowledge in programming and computer science, mathematics and statistics, as well as domain experience or subject matter expertise. And so, which is quite difficult most times. And so we find some people leaning at maybe one or two, and then maybe we might either fall in between programming and mathematics, which is more or less like machine learning and AI, or mathematics and subject matter, which is more or less like quantitative research. And the area that we term the danger zone, which is programming and subject matter expertise, because you actually, if you all you know as a data scientist is programming and the subject matter expertise without mathematics, it's really difficult. Like that's a very uncomfortable place for you to be. And so in order for us to like understand to work in teams, because we don't work in isolation, it becomes really, really important for data scientists to, as much as it can be cumbersome, but as much as you're trying to understand mathematics as well as subject matter or domain experience, it is very important for you to work and understand basic and essential best practices in programming in order for us to be able to work in teams, because data scientists do not work in isolation. So this gives like a typical example of the amount of persons, like what forms a team in order for you to come up with a working product. Say, for example, Netflix, or probably in any engineering company, like any company that does software engineering. So the core team mostly consists of the team lead, the project managers, software engineers, which include the front-end engineers, the back-end engineers, and the DevOps engineers. And then you have the data scientist, which is becoming really, really very important in most teams right now. And then you have the data engineers, which are focused on engineering data, ensuring that the data scientist has the data for him or her to work and build models. You have the UI UX designers. You have the solution architect, which is more or less like someone with more often than not is experienced in software engineering and can architect solutions to reduce downtime in prototyping, and as well as business analysts. So everyone works in tandem to ensure that we have a working product. And so that is why it is very important that we speak languages that we all understand. You know, there has to be some like overlapping of roles. And when you look at this team, you have the software engineers, data scientists, data engineers, they work closely together. And so more often than not, you have to like read each other's code. And it becomes really, really important that as you're contributing to the same code base, you need to have a uniform standard. You need to be writing maintainable code, reusable code that can be scaled. And these are some of the reasons why. So let's focus now on data scientist and ML engineer. The scope of work for data scientist and ML engineer, often it's broadly defined into just two, though it ranges from company to company, industry to industry. So this is not definitive. However, more often than not, it's more or less like the model development and prototyping, which involves analyzing data, deriving business insights, as well as prototyping models and doing some form of testing and evaluation. And the second phase involves the deployment and machine learning ops, which involves creating a pipeline for deploying the model at scale, model monitoring, continuous delivery, having a data feedback loop. That is really another important part, which is becoming more and more important by the day, because of most products are being productionalized. Most machine learning algorithms are being productionalized. So it's become really important that we have people that are skilled in MLOps, being able to productionalize machine learning models or machine learning systems effectively. And so we can roughly group that the data scientist is more or less focused on the first phase, while the machine learning engineers focus on the second phase. And before I say, but the reason I say this is there's often most times some confusion about if the data scientist is different from the machine learning engineers and the machine learning engineer is different from data scientists. And my understanding is it's a lot subjective, but I've seen a lot of people that agree with me. The data scientist is more or less focused on the first phase, which is analyzing data, prototyping models. Is heavy on the mathematics and understands how to build models like statistical models as well as deep learning models. However, the machine learning engineer has more background in software engineering as well as um, machine learning. And so it's focused on productionalizing machine learning models. And so they work in tandem with each other to ensure that this uh, you have like a machine learning system and a pipeline. But the interesting thing is that sometimes in some company, depending on the scope of the company, you'd have to like work and take both roles. So it's a lot, like I said, it's subjective. Okay. Okay, so let's move on to some of the um, essential software engineering best practices for data scientists and engineers. Um, in summary, it might seem some like it's one thing that we need to understand as data scientists and machine learning engineers is that we need to at the center of it all, we need to be able to write clean, stable, reusable code that can be maintained for years and easily scalable. Um, why do we have to do this? Because sometimes we might be it's very easy for you to get so um, fuzzy in the details of trying to experiment different models, and then not right. The models at the end of the day would not remain in your laptops. Would have to be used. It has to be fair for consumers. And so it becomes really important that it's good, since these models are going to be integrated in systems, it should be able to work optimally. And so, like I said, we have to work with the software engineers as well as machine learning, other members of the team to ensure that we meet our overall objective. And so in order for you to integrate your code to the code base, it has to meet like standard, like being clean, stable, reusable, as well as maintainable and easily scalable. And so some of the best practices include readable, efficient, and maintainable code, um, properly documented code, proper versioning. By versioning includes data versioning, source code versioning, as well as dependency management, as well as model versioning, and good dependency management because you most likely would be working with others, and so we need to manage dependencies very well in terms of like environments and generally all dependencies that you use in coming up with a solution, efficient testing, as well as efficient CI/CD implementation. That's continuous integration and continuous delivery, continuous deployment. So these are the best, some of the things that we're going to be looking at, some of the points, best practices that we're going to be looking at. And hopefully when we go through the demo, we will be able to see some of these in details of how we can really implement it and see why we we need to as data scientists, as machine learning engineers, you need to work to ensure that you write efficient code. So let's look at what do we define as readable code. When we talk about best practices for readable and maintainable code, most machine learning engineers and data scientists generally make use of Python. Um, although there are a lot of people that use R and maybe Julia, but Python is still like largely the most used language for data scientists, I'll argue. And so this presentation is really strictly based on, in terms of the guide and everything, based on Python. And so for maintaining readable and maintainable code, some of the recommendations, like some of the best practices includes using a style guide. For example, you can use this style guide for Python. Generally, it's PEP 8. If we are not conversant with it, and so I'm going to be sharing this slide. So yes, you can click on the link, but you can also research PEP 8 as well as there's also the Google style guide, which is pretty good. So that's why it's included here also. And then what really makes it easy in order for us as data scientists and machine learning engineers to be able to use the style guide effectively and to be properly guided, there are like extensions and IDs, like the VS Code. You have several extensions that can guide you to ensure that you're using um, the right style. Like you have linters and all that. So you have pilings that helps you to see, ensure that you're writing, maintaining convention. And so it's pretty cool that these are some of the things that we have like a style guide, so it can be readable by everyone. Um, the next thing, that's the naming convention. And so ideally, the classes, variables, and parameters should be nouns. When I mean nouns, like it should be, say for example, you're dealing with a person, or you're dealing with uh, a school, or you're building something, your classes should be named as a noun, while methods are generally like behaviors and so should be verbs. And as much as possible, should avoid abbreviations, except abbreviations that are usually universally known. And so naming convention is also very important because you want to be able to write and be able to share your code for everyone to understand. Um, and also for you to understand after a couple of years. And so it's really very important because it's we've most of the time had the experience where maybe after some months or even years, and you look at code you've written before, you say, well, how did I write this? Or I'm not sure the one that wrote this. And so it becomes really, really important for us to be able to write, ensure they maintain the naming conventions, classes, methods, as well as functions. So talking about functions like methods and classes, this is an example of this is an example of a function, def id checker. And so you can see that the naming convention here for methods, it's um, should it's more or less like a verb, like telling you that it's checking something like an ID checker. And then it gets the we're going to be talking more about doc strings, how to use doc strings like in documentation. So I'll come to that. But this is just a snippet of a function. And if a method or a function, method as in used in classes and function if used independently, should be easily described should be an easily described functionality. So when I say easily described functionality, what do I mean? It shouldn't be ambiguous. It shouldn't be something that one would have to think twice of, like think twice in order to understand. And so it should be something that is easily described. For example, identifier checker. So you can tell from the name that the method is used for checking for identifiers. It should be reusable throughout the project. And so when you write methods, you would want them, or even functions, you want to make them reusable. And so this is part of what we're talking about, writing reusable code. That's one reason why we have methods and classes. Writing functions rather than just maybe writing what a lot of people call spaghetti code. A method should handle a single thing. Yeah, so a method shouldn't be crowded. When I mean crowded, in the sense that one method does too many things. It makes it like I said, it increases ambiguity, and it makes your code not like readable. So as much as possible, you try to see how you can abstract, and it should provide a useful output. So although there are functions that do not return like an output, however, most functions do like return outputs, and so it should return a useful output. Um, Classes and objects, any unrelated functionality in your class. Avoid using unrelated functionality in your class. So if you have a class, like if the functions in a class, like the methods in a class, they should be related to each other, and it shouldn't just be like them. So it's one of the 5 single responsibility principle, one of the 5 principles of software design patterns. So you allow your code like a class to be able to handle one responsibility and not crowd it with so many things. And as much as possible, for methods, or for areas, like maybe you want to write a function and you see that, or you want to write a method in a class and you see that it's unrelated to that class or an object, it is important, or it's advisable for you to write them as functions, standalone functions. And so these are some of there are many others, but these are some of the key practices that are encouraged in order for us to write readable and maintainable code. Okay, good. So let's take a look at documentation. Now, this is something that sometimes after doing a lot of work and trying to think through the problem solving, sometimes we have the habit of not documenting our code properly. The thing is, in less than a year time, like I said, you're working in a team. It's really very important that you document your code the right way in order for others to be able to consume the same and to read the code, and also for maintainability. So use of doc strings is very important in classes. What are doc strings? So you can see this 3 quotation marks here and the one that ends at the bottom. So everything encapsulated in between, they're like comments that tells you about this function. And this is what constitutes a doc string. And so for method and functions, you have like a brief description, or like a definition of your function. And then you have like the parameters. If the function or the method has a parameter, right? It has the function, the description of the argument or the parameter, as well as the data structure associated with the parameter. Also, it has to give an insight into, like, you have to list out the description of the output, like what does the function return. If it returns nothing, you have to put it there, and also you have to put the type of like the data structure of what it's been returned. And lastly, description of error or exceptions with reason. So if there are going to be exceptions or errors, possible errors, you should also list it. So this is an example here on the other side of this slide also, that for a doc string. Now there's a little bit difference when it comes to, like, for classes. For classes, just a brief description of the class is sufficient, as well as using the doc strings for constructor method as well as the other methods in the class. Now, besides making it readable for your team members and maybe for yourself in the future, doc strings are really, really important, an important part of your code base, because with packages like Splints, you can auto-generate HTML-based documentation for users of APIs. And so if you maintain habits of always using doc strings for your functions, your methods, as well as your classes, it's something that will pay off in the long run. It's a very good habit. Also, there is also the repository and component level documentation. And so what do we mean by this? One of the most widely used version control systems is GitHub. And so then GitHub, like in other version controls or repositories, you have like a README that gives a description of the purpose of that repository. And so the it is important that you write a very good README. If you give a good description of the purpose of the project, anything like the most important parts of the project and things that are relating to the project, as well as license and I'm going to be showing you some examples. So we'll get there. But having a very good README helps, especially when you're putting it in you're open sourcing, you putting it in open source, and a lot of persons would have to work on it. So it gives it makes a good way for you to like get started on working on a project. And then the README, it's not so there is the README for the repository. However, if your project has several components, by components you have like folders, and in those folders you have folders. At each level of your directory, you should also have like a README, because the more complex the project is, the more it becomes difficult for someone just getting to understand the code base. The more it becomes difficult for the person to understand the code base. And so putting a very good README, like a documentation in the components level aspect, helps to let everyone get started on the project easily. So it's something that's very important, documentation. Also, something that I have not put here that is quite important also, it's although it shouldn't be so much, it shouldn't be abused, because sometimes it's being abused, except maybe you're using it for tutorial purpose only. But writing line comments like the one in the slide right now gets the identifiers. Writing comments also helps to provide perspective. However, it should be used with caution, because you wouldn't want to explain your code all the way. It's bad practice if you have to explain your code all the way. It means that maybe the code is not properly written. The code should speak for itself. The most exception, or the only exception, is when probably it's being used for maybe a tutorial purpose, and you want to explain every bit of it for maybe the learners to understand, and that is that's really acceptable. However, if you're looking at the production setting, we should be writing efficient code that doesn't really need much explanation. Writing clean and maintainable code that any software engineer that looks at it, any data scientist that looks at it will be able to like understand what's going on in terms of using the right variable names, using the right conventions. You would not have to explain much of your code. And also in terms of the logic also. So that's it with documentation. So let's talk about dependency management. And one thing that is really important for data scientists and machine learning engineers, especially like when you build a model. Yeah, it's important that your model runs anywhere, or any builds, being it a software, runs anywhere and is stable over time across any environment or several environments. And it's one reason why we need to pay attention to the dependencies. And when we say dependencies, yeah, like that the packages, say for example, I'm installing pandas or I'm installing NumPy. There are a couple of other packages that may be attached to it. There are other packages that are attached to it or that needs to be installed along with it. So these constitutes like there are like several dependencies. And so PEEP is the most popular dependency manager for Python. It's one of the most widely used. However, there are other dependencies um, like poetry and I think pip env. And so one thing that it's equally important in using dependency managers is that when um, it is important that when you use, like, for example, you're using pip, which is one of the most popular dependency managers, like I said earlier, the you should have, it is recommended that you have a requirements.txt file that records all the project dependencies. So say, for example, on my local machine, I'm using pandas, I'm using numpy, and in addition to that, I'm making use of a couple of other packages. Maybe outside scikit-learn, I decided to use maybe an XGBoost classifier. Um, I decided to use some other packages. Now the thing is, you're working in a team, and it's important that the someone else that needs to run that same build in his own machine will be able to replicate the same results that you have. And so that is why it is important for you to record all project dependencies in the requirements.txt file in the case of pip. So with the exact version of the package that has been specified. So it is important that when someone else maybe pulls your code and the person is going through, and the person can just install the requirements.txt files, and if there are packages that the person does not have in his or her machine, or that is not available in the other environment, it can be installed, so the build or whatever the work you've done will be can be replicated. Um, so pip, like I said, it's one of the most common dependency managers. But poetry is also becoming widespread because of its simplicity. Um, one major advantage it has, it also creates a virtual environment, and we can it like adds and removes package from its project file, which is kind of similar to the requirements.txt file that I talked about, that I mentioned for pip. And so there's a widespread adoption for poetry. And I think it's something that maybe you would want to look at. But the most important thing is ensuring that you have you list out ensure that the dependencies are properly managed. And for things like config files, they should be .env or .json. And so this involves like ensuring that uh, you properly manage your dependencies, like all configuration files, so that it can be replicable in another environment or in another machine. Okay. So let's talk about versioning. So the machine-wide versioning, a lot of people, yeah, it's very important for data scientists to version your code, and not just code, but we should understand that the machine learning system entails beyond just the source code. It involves data, the source code, as well as the model. And so you have like source code versioning, which is like you can use like a source code management, like sort of like Git, um, like a version control already, which is very popular. Um, and then for data versioning, you could use an open source platform like data versioning control, DVC, or MLflow. And then for model versioning also, you can use MLflow. Now the thing is, a lot of people talk about maybe using data versioning like DVC for model versioning, but it's not advisable. Reason being, it's really difficult for you to separate the data versioning aspect of it from the model versioning, and it doesn't make sense for you to put like your input and your output in the same um, version control system. Not really version control system, but in the same package. And so it is bad practice. It's considered bad practice for you to version your model using DVC. One thing also that you need to understand, it's DVC. It works closely, like it works with Git, and so while we are doing a case study, we'll have some time to like delve into DVC and see how it works. Okay. Um, and so for Git, it's also important to exclude files which are not relevant to the project. Say, for example, um, you're using VS Code and there are a lot of config files. There are some other dependencies in your development environment that are not important or not required, or you think it's not important for production or maybe for other members of your team. You include that in your git ignore file, so it's not committed to the repository. Um, Again, during a case study, we'll have enough time to like go through that. One thing I'd want to mention is I've been talking about more about like open source technologies, primarily because I feel it's for anyone getting started, that's where you should probably start from. My opinion though, because it's like I said, it's open source, and so it's easy to get, not just sometimes might not be easy to get started on, but it's easily accessible as well, as opposed to some of these services that may have charges. And so that doesn't rule out cloud solutions that have self-managed services that handle both code, data, and model versioning, like Amazon SageMaker, Azure Machine Learning, as well as IBM Watson. And so at the end of the presentation, we're going to be talking briefly about like how, not necessarily versioning, but how the architecture works in some of these, just one of these cloud solutions. Okay. So another important aspect of another best practice that data scientists and machine learning engineers should take seriously is testing. So this is something that even sometimes as developers, maybe as software engineers, there are a lot of people that probably, it's considered really bad practice if you don't test your code. And as data scientists, sometimes we shy away from wanting to test our code. We feel like, no, it's not necessary. But the thing is, the importance of testing codes cannot be emphasized, because you want something that has been deployed to production, and you wouldn't want the code, you want it to be maintainable, something that would not break the system. And so just one weak link can cause a problem, and then everything goes down. And so it's important that everything that goes into production, it's tested and ensure that it meets the quality standards, not just in terms of like quality assurance, but in terms of ensuring that it meets like best practice. And so there are several levels of testing. The first being unit testing. So unit testing involves testing individual units of the software to validate that the tested units meet its design specification. So what do we mean by that? So you have to test functions, methods that you built in your code. These are like small chunks, and so it's important for you to ensure that at that low level, at the bottom level, that every unit of the software is working. The next is integration testing. Now, integration testing involves testing the combined individual units of the software as a group. And so we talked about like testing functions and methods. However, we are talking about like bringing them together, bringing everything together, bringing the software together, and then seeing, testing it with how it works with other parts of the software. So that is more or less like testing it as a group. So that's what integration testing involves. System testing involves end-to-end testing of system specifications. So there's something I didn't really mention that I think I missed out, which is still important, although it's not apparent in most teams, but there are teams that have like QA engineers, like testers, dedicated testers. And most times this is what you do, like beyond the more often than not go into that level of like unit testing, but they carry out system testing involving end-to-end testing of the system specifications to ensure that everything is working the way it should be. And the last, I'm going to talking about when it comes to testing, it's drift testing and sim testing. So this is more or less if it's more or less concerned and it's more or less directed to like machine learning engineers and data scientists. So when I say drift testing, I mean you have KPIs. Maybe the KPIs could be accuracy, it could be some metrics. And so when the model is in production, a model has been deployed in production, it has to be monitored to ensure that it doesn't drift from these KPIs, to ensure that whatever metrics you set, it doesn't go beyond them. And so it is important to carry out automated testing to ensure, and when it maybe the model falls beyond or below the KPI, it sends like a notification or it triggers a rollback to a previous version. And so that is also important. Some other form of testing, it's sim testing. Not really common to, but it's also like a kind of unit testing or data outputs and inputs to ensure that the model lies within maybe like within a defined tolerance. And so this is also like a machine learning directly related to testing machine learning models. And so you just test like inputs and get your outputs and try to see that, well, what's the error margin and is it within like a tolerance and accepted range. There are many other forms of like testing that are kind of geared towards machine learning, and it's increasing by the day because productionizing machine learning models has really been on the rise in the last few years, and a lot of development has been going around in MLOps. And so there are several metrics, there are several dimensions that are being monitored to ensure that the model is performing as it should be. And so the MLOps engineer or whoever handles MLOps, the machine learning engineer, has a lot of work to ensure that, which varies from industry to industry and from project to project, to ensure that the model keeps working efficiently or as it should. Okay, so with that, I think we are done with testing. So I think the last aspect I'm going to be talking about, which we might not really dig deep into, because like I said, the focus of this presentation is going to be the first phase of the scope of work for data scientists and machine learning engineers. However, it's still important for data scientists and machine learning engineers to understand automation. Now, even if you are not going to, you might have like someone in your team or maybe a dedicated DevOps engineer or ML ops engineer whatever title is given that would set up like these pipelines. It's still important for you to be aware of how this works. And like I said, again, it varies from team. You might have to wear many hats sometimes. And so continuous integration, continuous deployment is implemented to like build, test, and safely deploy your application so you can iterate quickly. And so what this means is you don't have to like build your model and send your model over Slack, probably, and um, give it to the DevOps guy to work on like productionalizing it. So continuous integration, continuous deployments involves new builds and automated testing, automated like continuous integration immediately as code is merged. Maybe a new model has been deployed or you've um, a new commit or sorry, a new pull request has been merged to the master branch. The moment it has been merged, it's an automated testing is initiated and new builds is created and automated testing is initiated. Um, if it passes all tests, the continuous deployment begins. However, if it doesn't, then the engineer, the software engineer or data scientist involved would have to like work on the code to see what's wrong to ensure that it passes the test. Now, for continuous deployment, it deploys changes automatically to production. Um, so you have a model like a trained model. It's now served as a prediction service for predictions, which is something that's still very close to what I said when it came to testing. You need to track like summary statistics of the live data to ensure that you're not deviating from the set performance like the KPIs or the metrics of the model. And so this involves like sometimes ensuring that there is like we set the when the model starts performing poorly based on maybe live data, it sends like notification or it rolls back to a previous version of the model. Now, a lot of these are becoming really, like I said, this is like all part of ensuring that this section of your deployment, like integration and deployment, is being automated. And there are a lot of work, a lot of people talking about like a lot of buzzwords are talking about AutoML and how it's going to even beyond CI/CD, also some aspect of data scientist, like maybe data cleaning and all that. The thing is, yeah, AutoML has a lot of potential, but for me, I think it's still very important for the data scientists to like work and see the data scientists will still have to like do a lot of work even with implementation of AutoML. And so that's why it's really very important for you to understand these principles. And more often than not, you'd have to implement them. So to wrap it up, we've talked about like several best practices. We talked about uh, being code being readable, efficient, and maintainable, having proper documentation, proper versioning, as well as good dependency management and efficient testing, and also like having efficient CI/CD. Um, the objective of it all is to ensure that we have like a clean, stable, reusable code that is maintainable for a period of time and it's easily scalable so production doesn't break. Um, Now I'm going to take some time to talk about the case study. Some of these practices, I feel it should be more practical, trying to see how we can implement some of these services, and these best practices. And why it's not going to be exhaustive, so this case study is going to like show us how important or why it is important for us to adopt these best practices and ensure that you can work with other people in a team. And so I'm going to be working on the project. It's Goodreads average rating prediction. So Goodreads is an American social cataloging website. It's very popular, and individuals like can search freely for books, quotes, and reviews. And it's something that like contains a database of it has a very large database of books, annotations, and quotes. And the project we're going to be working through, it's um, going to be the objective of the project is to predict the average rating of a book. And so this it has like books have different features, and then the average rating of different books ranges from 1 to 5, and several features from the book and data sets are like generated and explored, and it's more or less like a classification task. And so I'm going to be exiting the slide right now, so we can get through to the code.